lab, equilibrium principle with Chateliers and the Chateliers principle. Here's what it is. If an equilibrium system is subjected to a stress, the system will react to remove the stress. It sounds like one of Newton's laws, right? So like the equal or opposite reaction. Read a bit more. To remove a stress, a system can only do one of two things: form more products using up reactants, or reverse the direction, form more reactants using up products. This experiment will form several equilibrium systems, then by putting different stresses on, we'll observe. We're only going to do one of them. I already did the one the first day on the overhead projector in the Petri dishes. We're going to skip the first two, just the way these points work. So, sorry. Okay, we'll talk about it this way. This is the one we did already, so I'm going to just talk about this a little bit, okay? This is that iron, which was rusty, orange, gold colored. SCN was the colorless stuff. FeSCN was the red brown. It looked like blood, right? Okay. Do you guys remember how this worked? Now, the Chateliers principle is basically understanding equilibrium without doing any real. Now think about this. This is at equilibrium, let's suppose, and it's just a steady current. What if I have an initial change where I say initially I remove initially remove nothing. You can just pay attention. You don't have to copy it. All of a sudden, this balance that we had in the equilibrium is upset. And according to the Chateliers principle, the system's going to react to counteract it. Right? So, how will it do that? If your initial thing is to remove iron, the system has to figure out how to replace lost iron. First of all, I always think, which way does the reaction shift? Left, reverse, or right, forward? To make more iron to replace the lost stuff, which way does the reaction have to shift? That, right? Okay? And the people are recording this. It has to shift this way. It'll still be going this way a little bit, but to reset the equilibrium, it's going to have to shift to the left to make more iron, right? If it's going to go to the left and make more iron, what else is it making? Yeah, the SCN. So what's going to happen as a result is when it replaces the lost iron, it's going to increase the SCN. And in order to do that, it has to decrease or use up this product. Right? Follow that reasoning? Let's just try something different. This is what we did that when we added a chemical and became clear, like colors. What if my initial change was to I'll put is add more SCN negative. That was one of the things I started out with. Well, all of a sudden, it was at an equilibrium and it was carefully balanced out. And you've got too much SCN. To use up the excess SCN, which way does this reaction have to switch? Forward or reverse? The only way to use it up is actually no, to go forward. So as a result of this initial change, it's going to use up this excess SCN by going forward or to the right. In that process, it's going to make more or increase the product. And it will use up or decrease, as a byproduct, it will decrease the amount of iron. And we saw that. these are the kind of things we're going to do in our lab. Where you guys actually get to do instead of me on an overhead. Okay, so that's what we saw about, well, first day. So you're going to flip to the back thing, right? Inquiry. Equilibrium with cobalt complex ions. If you're watching this on video, you don't have this sheet yet. You'll pick it up and we'll see about arranging for some time for you to do this right now. Now, this is one of the very few times that we have solutions that are not aqueous, not water-based. You must have Al, alcohol. It's an alcohol-based. I've dissolved that in instead of water. It just works better. So because we're using ethanol, it's black, and we're going to want to heat stuff up, we are not going to use any flames to heat it up. I have a kettle over there. I'm going to just put stuff into test tubes, warm them up with salt. Right? Safe. There's going to be dropper bottles that are dark. It's silver nitrate, and it stains clothing. So you got to be careful. Okay? There's very little chance. There's nothing that we're going to be heating with flames. There's no chance of really bubbling up and splashing into the pot. There's not inherent danger there, but we're going to wear glasses. You guys know where the soap is in this classroom over there. Use it if you need to. Measure about 50 mils of ethanol in a beaker. I'm making it up just because there's less handling and less touching. Now, when I said, how do we heat it up if we can't use a flame? You're going to put hot water into a beaker and then put your test tube into the hot water. Okay? That's it. I'm going to make this cobalt chloride mixture. You're going to create a procedure that will stress the equilibrium in the following ways, and you're going to figure out how each test is going to be performed. Predict the color of this, and kind of do it together. But the first two things are heating and cooling. I have ice for cooling. Now look at this equilibrium. You notice that heat. If you would have had physical science all year long, or all semester long last year, you would have learned endothermic and exothermic reactions. But all you really need to remember. Exothermic is where heat is exiting a system, and it's like an explosion, a fire. Those are very exothermic, right? Because they give off a lot of energy. This is an endothermic. The heat energy ends up inside. Sometimes those will feel really cold to the touch because it's drawing the heat energy from your hands. Some of it. Like, you know, sports injuries, you ever have those, they're room temperature and then you snap them and then they start to freeze? There's an endothermic reaction going on. It's drawing the heat from, which is good. Okay. So think of heat like a reactant when we predict it. The first thing we're going to test out is heating the system. It's like, if I initially add heat, which way does the reaction shift to get rid of the excess energy? To use up stuff, it has to go this way more than this way. That's the way it uses it. It'll get rid of the excess heat, and it'll make more of the product. And it'll decrease. It'll use up, in the process of using up heat, it's going to use up the Cl negative and the Cl, which is flow 6. Okay? These are the prediction things. Now, I'm going to pause this because video-wise, we're going to do an activity. There's not a lot you can see. Okay, we've done our lab. Now we're going to, what is it called? 3A? 3B, assignment 3B. And we're examining this reaction, N2O4 plus energy, 2NO2. We've started without the chlorine, so I'll just recap. 1, which side has more gas molecules, reactant or fine? The left side has 1 gas molecule versus the 2 on this side. So the product has more. we're just starting up, number 2. How would an increase in pressure affect this reaction? Increasing pressure is like reducing volume. It will favor the side with less gas molecules, so it will favor the reactants. Less gas molecules. Okay. What will happen to the concentration of N2O4 and NO2? If it's shifting to the left, it will favor the reactant. What do you get more? What do you get less? Yeah, the N2O4. So N2O4 will increase.
You always put them in brackets when you're writing.
Yes, because that means concentration of it. Right? I don't want to write out the word concentration. Concentration of NO2 decreases. Now here's something I didn't mention. N2O4 is colored. NO2 is brown, and I showed you the 2, right? Early. But what's going to happen to the color of the system then if it shifts left? Yeah, it'll, let's just say less intense brown. Yeah, because it's hard to measure. We're still looking at science catalogs for some kind of setup for this reaction. Okay, so we're like an adjustment. Oh, anyway, dream big. Don't give up on you guys' dreams, eh? Don't like it. Stay sleeping in the morning. Don't give up on your dreams. What do you mean? That's my grad thing. 21. Yeah. Like a homecoming of sorts. 30 years ago, I was pretty cool. Anyway, back to this. Oh. So, you guys got that down? I'm going to just clear it from this. That's ready for the next time. Just looking at this, right? Okay. Here's the second one. And actually, you just don't realize it maybe, but you should be somewhat familiar with this. This reaction occurs in carbonated drinks, so any pump. It's also in your bloodstream as a result of carbon dioxide. Well, respiration. Right. CO2 is dissolved in a water-based solution. You get carbonic acid. It's acidic. We don't need to know much about acids yet, but H plus means that it's going to be acidic. Yes? Or no, just stretch. So, have you ever, we'll talk about this. Which side has more gas particles? You've got to look at that first. Okay, I've got one gas particle in this balanced reaction. I got nothing on this side. So it's obvious the reactant is the only one with a gas particle, right? Yeah. No, on the right side, it's aqueous, it's not gas. As far as gas goes. Yeah.
there a difference between aqueous and liquid, or like how?
Yes, and here's what it is. Aqueous means dissolved in water. And that water is just pure water, like liquid.
Yeah, pure. Yeah, pure.
So it would make no sense to say aqueous water. Because water dissolves in water. And so the concentration of water, pure liquid, is 100% water. Whereas HCO3 minus aqueous, that'll be like, 1 mole in a liter, or you can change the concentration. That's what's important to know. Question.
My question was about earlier.
Okay.
I asked if water was wet.
Oh, you just, to which side would the, not control? Which side of the equilibrium shift if the pressure was increased? Then the side of the least gas particles. Which one is that? Right. Pretty obviously the product. I'll put it both ways, the right side, which means product. Then, what will happen to the concentration of each of the substances in the equation when they shift first? What will go up, what will go down? What decreases? Shifts to the left. Yeah, so we'll use the word reactants. So for reactants decrease, products increase. Now, I won't get into Ford too much, but how might you be able to tell, to detect if the equilibrium has shifted? More product, less reactant, whatever. Hint. Well, you measure the pH of the solution, basically, to see if the H plus has changed. I'll just say this. And we'll know more about pH in the acid base. So don't worry about it. Now, I want to return something. Because you're actually familiar with this something. Carbonated drinks. So let's think of 7-Up or Sprite in a plastic 2-liter bottle of yours, whatever, 500 ml bottle. I can't remember. Now, first thing, and it doesn't matter what pop. I chose 7-Up and Sprite because you can see it's color. Right? It's a easy drink, whatever, I don't know. Restaurant. That's a good restaurant. Now, have you ever tried to squeeze a pop bottle when it's right out of the store and never been opened? Or squeeze a pop can? How is it? Hard. It's really hard. It's highly pressurized. What happens immediately when you twist the cap off of a 2-liter of Sprite or anything? The gas is released. So it used to be a closed system. No gas could escape within reason. Then you open it up. All of a sudden, you've reduced the pressure dramatically. When you reduce the pressure on this reaction, which way does the equilibrium shift? To the reactant side, to the side with the more gas particles. There's more space for the CO2. Does it make sense? Why? Have you ever, before you've ever opened up a pop bottle, have you ever shaken it and it looks foamy and stuff? But then if you let it sit for a minute, all the gas bubbles return into circulating to the liquid, right? You actually can't see the gas. It's dissolved in the liquid. Only when you change the pressure do you see gas bubbles coming out of Sprite. You know exactly what it is, right? So that's, you've seen this equilibrium. That's also related to why, and I've never scuba dived in it. Anyways, but what do you guys know about somebody who's deep sea scuba diving? Can they swim straight up?
No.
No. It's the bends, they call it, right? And it's something to do with the gases in your bloodstream. The pressure changes. And you can kind of relate that because CO2 and oxygen being carried in the blood, right? It screws up the equilibrium. You have to do it slow. Also, incidentally, nothing to do with equilibrium. I noticed you pointing to your ears. Sometimes I get the loss, and if I'm swimming for a ring or something like this, my kids always used to be little. We dive, and then they throw something way super deep. You never get your ears even feeling like even if that's not too deep either. But you can do it without scuba. But it sometimes really hurts like that pressure change. I don't know. Anyways, I think anyways, just wondering if do you have some kind of ear protection when you do deep sea scuba diving?
When you wear like a suit, something like that, probably do it.
I don't know, like, but yeah, does it have special ear protectors? It just looks thin and flimsy. I have no idea.
So what would that do? Like just over there? I don't think anything.
Well, as long as it, because the inner ear, I don't know. I'm gonna stop. Okay. I'm just wondering aloud. Okay, I'll get this ready for the next page. So now, examine the following reactions. I'm going to get you guys to work with me. Predict the effect of increased pressure on these systems. So, the first one, you're going to look which side has more particles, right? And then, increased pressure favors the fewer one. Tell me about the first one. Increased pressure. Somebody on this side, there's 5 of them, someone come up with them. And you guys on the right side come up with an answer for B.
Right for your target.
Oh, my right side, yeah. So, Rachel, which side has more particles? So let's count. How many particles? 2, right? Plus 1, so there's 3 particles on the left. So 3 particles on this side versus 2 particles. Once you know that, you put the squeeze on it and increase pressure. Which side is favored? The one that takes up, when you have less space to put it in, it'll go to the side that takes up. So for, yes, now you think. So, I'm going to put this down like this. Increased pressure favors the product. Product is a singular. Now looking at question B. Here are the sample. How many particles on the left? And the right? 2. They're all gas. If there was a liquid in there, you wouldn't count. So does pressure favor either side? It's a tie, right? No effect. Pressure has no effect. Now, the last one. They're all gases, so just count them up. Increased pressure. Which side? In the middle, please.
The left side? Yeah.
So the left side has 4 particles, right? 4. This has 2. 3 hydrogens and 1. So there's your 4. Good thing we figured this out.
On the right side of that.
That's 1 particle of CH4 and 1 particle of water gas. So fewer particles on the right. 2 particles on the right versus 4 on the left.
Water, gas, or
Water vapor, water gas. Vapor is just the same word. Like it's the same.
yeah.
So increased pressure. Favors product. Now, the last thing I want you guys to do with me, work through this reaction. We'll do some predictions. I'm going to just put a line through here just so that I really get it in my head, the product inside and the reaction. Now the first one's all done for you. I'll go through CO rates. This is the initial change, what happens as a result. So let's go through. So initially, I increased the carbon monoxide. That's what I'm talking about, right? That means you have excess carbon monoxide. How does the system get rid of excess carbon monoxide? It shifts to the left or the right? That's outside. Got it. Anyways, all right, let's get back on. Does the reaction need to go this way to use up extra CO, or does it need to go left to use up extra CO? It needs to go forward to the right. I want you, even though it's not directly out, I want you to just do this. Right on this line here, just put an arrow that's a little bigger to the right than it is to the left. Just to say that because of that change, momentarily, it will shift. Does that make sense? To get rid of the extra CO. When you see CO raised, you just say, how do I do the opposite? How do I bring it back down? It shifts to the right. And when you shift something to the right, that means you're going to make more product. So raised. And when you do that, it's because you're using up that lower. So, goodbye, goodbye. So,
I literally told that you break out the song when you got it. I want
What are they doing for like this?
yeah, just to make sure it is. Yeah, too much more.
Yeah.
9 years old now. Get back to this. Heat atom. So we can treat heat like it's a chemical in the sense that temperature raised is adding heat, right? But it's increased something on the reactant side. We think, as soon as you see that, I just put a line, how do I undo that? How do I decrease it? How do you use up heat energy? Shifting to the left or the right? Got all this extra energy, so you go to the right, a little bit to the left, it's overpowering to the right. That means you're going to raise and lower. This is a fool's game. Here's what I'm going to do from now on. Watch this. Smart. Good. And then I'm going to make a corner. I'm going to save so much time. You'll see. Get back to this. This time it's a product. CH4 is raised. How does the reaction shift to get rid of the extra method? Yeah, it has to go in reverse direction. Get rid of the extra. Goes this way more than that way, right? Because you got extra on the right hand side. So you think, how do I undo that? So in the process of driving the reaction backwards, it will lower, and this is why I did this. Oh, smart board is the best thing. And the temperature, the heat energy is good. Go ahead, just say up, down if you want to say some time. Go ahead. Finally, one that's actually lowered. Different. The next one, H2O is lowered. So I think, how do I bring it back up? I've lost. Which way does the reaction have to drive to make more water? Forward. It goes more forward than reverse. That means it also increases or raises CH4, and it uses up all the reactants. Or it doesn't use it totally up. It lowers it. Last three. Time for the end. When H2 is lowered, H2 is a reactant. I got to bring it back up. How does the reaction go to then make more of a reactant? It goes in reverse. So I'm going to put this here to say it goes more to the left than it does to the right. Sometimes I'll ask the shift left and right. So then we're going to make more of all the other reactants as well, using up. And we just practiced this one, pressure. We started with more gas particles. The left has CO plus 3H2, so 4, versus 2 on the right. So increase in pressure will shift things to the right, less space. So it comes to a new balance. Reaction rates going forward and reverse are the same. That's what people are doing. Now, catalyst is a word you may recall from grade 10, you may not. In biology, biological catalyst is called an enzyme. You guys ever seen sugar bread? Yeah, it's stinky, but it's really hot to do it, right? Yes, when I eat, things will fill the sugar, so I get energy. My body is doing that reaction at a much lower temperature, right? There's some biological enzymes, some pathways that allow reactions to happen in the body at 37 degrees Celsius. The reason the temperature. What do catalysts do? They can increase the speed of reaction, reducing energy requirements. How they do it? If it's increasing the speed of the reaction in the form of one volt, a catalyst will also increase the speed of the reaction to the left. It doesn't have an effect in this way. No change. Okay. Now that wraps up. You can now finish the assignment, everything except for the very last page. You know what? I've decided I'm not going to get into that type of problem just for the time constraints we have with this. Okay? So the unit assignment, we'll talk about it on for you guys Monday. You guys can wrap some things up and we'll be it'll be due probably the Wednesday. But I'll check in with you guys on the Monday. Okay? So get working on that unit assignment. Go on. Everything but the last page. Monday we'll check in about it to see if it's brief.